students. Today we are going to discuss about Unit 4 Physics, Electromagnetic Inductions and Alternating Current. In this unit, the student is exposed to the phenomena of electromagnetic inductions, the application of Lenz's law to find the direction of induced EMF, the concept of eddy current and its uses, the phenomena of self-inductions and mutual inductions and etc. Now, first topic electromagnetic induction. 7 subdivisions here. First topic introductions, magnetic flux, Faraday's experiment on electromagnetic inductions, first experiment, second experiment, Lenz's law, conservation of energy, and etc. Now, what is the electromagnetic inductions? Introductions. In the previous chapter, we have learned that whenever an electric current flows through the conductor, it produces a magnetic field around it. This was discovered by Christian Ost. Later, Ampere proved that a current carrying loop behaves like a bar magnet. These are the magnetic effect produced by the electric current. Physicists then began to think of conserve energy. The experiments were done by Michael Faraday of UK and Joseph Henry of USA. This attempt became successful and led to the discovery of phenomena called electromagnetic inductions. Michael Faraday is credited with the discovery of electromagnetic inductions in 1831. In this chapter, let us see the few experiments of Faraday, the result and the phenomena of electromagnetic inductions. Before that, we will recollect the concept magnetic flux linked with a surface of area. Next, magnetic flux. See the video. Magnetic flux 5b. The magnetic flux through an area A in the magnetic field is defined as the number of magnetic field lines passing through the area normally and is given by the equation pi b is equal to integration of b vector dot dA vector, that is equal to BA cos theta, where the integral is taken over the area A and theta is the angle between the direction of magnetic field and the outward normal to the area. The magnetic field is B vector is uniform over the area A and is perpendicular to the area show the figure. Then the above the equations pi b is equal to BA. The theta is equal to 0, cos theta is equal to 1. Pi b is equal to BA. This SI unit of magnetic flux is Tm square. It is show the measure in the Weber or Web. 1 Web is equal to 1 Tm square. Faraday's experiment on electromagnetic inductions. First experiment. Consider a closed circuit consisting of a coil C of insulated wire and a galvanometer G as shown the figure. The galvanometer does not indicate deflections as there is no electric current in the circuit. When a bar magnet is inserted into the stationary coil, with its north pole facing the coil, there is a momentary deflection in the galvanometer. This indicates that the electric current is set up in the coil. If the magnet is kept stationary inside the coil, the galvanometer does not indicate deflection. The bar magnet is now withdrawn from the coil. The galvanometer again gives the momentary deflection but in the opposite direction. So, the electric current flow opposite direction. Now, if the magnet is moved faster, it gives a larger deflection due to the greater current in the circuit. The bar magnet is reversed, that is, the south pole now faces the coil. When the experiment is repeated, the deflections are opposite to the obtained in the case of north pole. If the magnet is kept stationary and the coil is moved towards or away from the coil, similarly, the results are obtained. It is concluded that whenever there is a relative motion between the coil and the magnet, There is a deflection in the galvanometer indicating the electric current set up in the coil. Now, the second experiment of electromagnetic induction of Faraday's law. The second experiment considered two closed circuits show the figures. A circuit consists of a coil P primary, a battery B, a key K is called the primary circuit, while a circuit holds a coil S and the galvanometer G is known as secondary coil. A coil P and S are kept or rest closed promiscuously of respect to one of another. If the primary circuit is closed, the electric current starts flow the primary circuit. At the time, the galvanometer gives a momentary deflection. After that, when the electric current reaches the certain steady values, no deflection, it is observed the galvanometer. Likewise, the primary circuit is broken. The electric current started decreasing, and there is again the sudden deflection, but in the opposite direction. When the electric current becomes zero, the galvanometer shows no deflection. From the above the observation, it is concluded that whenever the electric current in the primary circuit changes, the galvanometer shows the deflection. Faraday's law of electromagnetic inductions. From the result of his experiment, Faraday realized that based on this idea, Faraday's experiments are understood in the following way. In the first experiment, when a bore magnet is placed close to the coil, some of the magnetic field lines of the bore magnet pass through the coil. That is, the magnetic flux is linked with the coil. When the bore magnet and the coil approach each other, the magnetic flux linked with the coil increases. So this increases the magnetic flux indicated as EMF, electromagnetic force, and hence the transistor's electric current flow in the circuit in one direction. At the same time, when the residues away from one another, the magnetic flux linked with a coil decreases. The decrease the magnetic flux again induces an EMF opposite direction. Hence the electric current flow the opposite direction. So there is a deflection in the galvanometer when there is a relative motion between the coil and magnet. In the second experiment, when the primary coil P carried the electric current, a magnetic field established around it. The magnetic lines of this field passes through the itself and a neighboring secondary coil S. When the primary coil is open, no electric current flow. At the ends of the magnetic flux linked with the secondary coil is zero. However, when the primary circuit is closed, the increase the current built up the magnetic field around the primary coil. Therefore, the magnetic flux linked with the secondary coil. Third one, subdivision. Faraday's law of electromagnetic induction. What is the Faraday's law of electromagnetic inductions? Whenever the magnetic flux linked with a closed coil changes, an EMF is induced and the hands-on electric current flow in the circuit. This current is called an induced current, and the EMF given rise to such a current is called an induced EMF. This phenomena is known as electromagnetic inductions. This is here some of the explanation of the experiment. Now, finally, the conclusions of Faraday's experiment are stated as two laws, the first law and second law. What is the first law of Faraday's? The Faraday's first law, whenever magnetic flux linked with a closed circuit changes, an EMF is induced in the electric current. Again, the first law, whenever magnetic flux linked with a closed circuit changes, an EMF is induced in the circuit. Second law, the magnitude of a induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. If the magnetic flux linked with a coil changes by d phi b in the time dt, then the induced EMF is given by E is equal to minus d phi b divided by dt. E equals minus of capital N d pi b divided by dt. E is equal to minus d into N pi b divided by dt. Here N d pi is called flux linkage. Defined as the product of number of the turn N of the coil and the magnetic flux. The linking each turn of the coil pi b. That's all over. Tick பண்ணிடு.